Uh, everyone, my name is Mitya. I'm working on computer vision things. I like computer vision a lot. I work with a lot of things related to 3D construction. I'm going to talk in English, and I'm going to cover a lot of topics. I won't go really deep technically into it, but there's going to be a link to the presentation in the end. So where we're at right now is I want to talk about 3D construction and where we're at right now and how we got to this point. Like a month ago, this is very recent. Meta Labs, their AI labs released this SAM 3D model, which is an extension of their simulation models, which just does direct image to 3D conversion. Just a huge transformer that takes an image, outputs a 3D model. And this is just something very new, something that wasn't possible at all previously. But this is a little bit to the side. We're going to talk about more 3D construction in the sense of working with multiple images. So for example, here's me just taking a video at my house of just a simple toy that I have. And there's this convenient app called Luma AI, which just from a phone scan lets you convert it to this 3D model, export it as a mesh, use it, I don't know, in a game, in anything. A mesh is something that you can use basically anywhere where you work with 3D models. And this is viewable in real time in 3D. And it's something very, very interesting. This app and this technology is also used for large, very photorealistic 3D constructions, which I think is really cool. There's really interesting algorithms behind it, but there was history, all kinds of things that came before we got to this point. And so I want to talk about 3D construction and how we got to the photorealistic castles that we had before. Why we even talk about this and why I think this is interesting. We as humans, it's very easy for us to see it with our eyes and get some 3D understanding of the world around us. For computers, it's not that easy. First, we need multiple images because we have no structure in 2D images whatsoever. We just have pixels and mapping to RGB, just brightness basically. No information about structure at all. And we need to somehow teach computers to think about how to extract, how far objects are away from each other, and stuff like that. The backbone idea for it is just finding common control points between different images, trying to match them, recover this into some kind of 3D model, both for the object and for the cameras. But this is just general ideas. I'm not only able to go very deep into it.
Sorry, are you showing us SFM or a rendering?
I'm talking about SFM, structure from motion, right? Multiple images, out we get a 3D model. It started all when I did the research for it. The earliest mention I could find of some algorithms like that in 1958, something by the US Air Force. They did cartography. They wanted to get measurements of things on land, and they had aerial images, and they wanted to do computation based on that. And there was no automation whatsoever. This was just manual computations, but still there was some interesting theory there to then support future advancements. And then, a little bit of a time skip, we're at 1981, where we have already some automated methods. This is a paper called Random Sample Consensus for automated cartography. This is a paper that first kind of managed to make this work on actual real data with noisy measurements, with outlier measurements. And for some reason, it's very significant, 30K citations. That's huge. Well, turns out it's RANZAC. I don't know if the name is familiar to you. This is becoming very popular in data science. This is this method that lets you fit statistical models to very noisy data or which has a lot of outliers. It's used basically everywhere now. Not only computer vision, in all kinds of places. In computer vision, it's very, very crucial because we have a lot of noisy measurements, noisy data. But this is just interesting that a huge milestone in computer vision was this RANZAC that is now basically important for everything, for a lot of things. And somewhere in the 80s and 90s, all around the world, there was a lot of investment into robotics. With robotics, you have this need for real-time navigation, real-time exploration of the space around the robots. And there was big projects into autonomous driving, into drone navigation, underwater exploration, which all led to a huge technological feat. which is SLAM, or visual odometry. Like, basically, it's just names for the same thing, where we have real-time navigation and mapping of the surrounding space just based on visual data, which was huge. It's like it's a huge engineering feat. A lot of hardware optimizations, a lot of very smart use of the hardware at the time. And this is now the backbone of all robotics navigation. This is now the backbone of all AR applications or VR applications, because same thing, you have like a device that gives you visual data and you want to understand your position in 3D space. Like something like Pokemon Go, where you want to have Pokemon stay in the same place where it was initially positioned. For VR headsets, I'm also a developer of VR. There's also a lot of interesting technology there. There's like 5 different cameras, all supporting real-time mapping and tracking of your movements. And so this was like a huge leap in technological advancements for like basically real-time reconstruction kind of, but it's still only very rough mapping of the surroundings. It's not really usable for creating 3D models, for actually reconstruction. So, which is why a lot of projects want to work on something better than this. So, for example, there was this really interesting project in phototourism called phototourism, which took huge collections of images from online. For example, this is a cool example of Notre Dame. Just taking 2.6K tourist photos, feeding them into a program that does very robust filtering, processing of the data, and gives you like a whole full 3D model, just this point cloud, positions every tourist photo in 3D space where it was taken from, and lets you explore it. Sadly, I don't think it's very much open source. I think you can explore this software right now, but it just looks very cool. 5K citations, I think it also proves that it's pretty significant. It solves a lot of problems at the time. And now we're like already at a point where we need to optimize this. So this is 2.6K photos and gives us a great model, but this takes 2 weeks to reconstruct this. We can't work with this. And a lot of researchers for a lot of time worked on this. This is again a time skip into 2016. This is a huge, very cool example. Just feeding 75K tourist photos from Rome into just a huge program, into like this huge reconstruction that is done like 3 hours. It's pretty quick. We get a huge reconstruction of Rome, a specific neighborhood around the Colosseum. And this is again a huge technological feat. This did take like a pretty big machine to reconstruct, but still we managed to process 30 times as many photos in much less time. This software HoloMap is now like the golden standard in photogrammetry. If you work in any way with 3D reconstruction, or you need to implement something of your own, if you read any paper, they're going to mention HoloMap because now everyone uses it. It's like this open source project that is very, very easy to tune, easy to basically tune for your needs, basically. But the problem is that this approach still gives us these sparse point clouds. It's not really usable for visually pleasing 3D models. Like there's a lot of gaps, a lot of just points hanging in space. Together with HoloMap, they also released the solution to that. There's it's like a set of algorithms called multi-view stereo, which basically just solves the problem of that. We have this very sparse reconstruction from before, but then we can upgrade that into this very dense reconstruction, where we have either just a very dense, like almost no gaps 3D point cloud, or just a full-on mesh that we can then use in downstream applications like game development, robotic simulations. Basically, this is actually like a mesh. Surfaces like this is something that is used in all kinds of 3D applications, whereas point clouds aren't really usable.
What kind of a mesh? Is it triangulated?
Yeah, it's just algorithms that can work with very dense point clouds like this into meshes. It's built into HoloMap also. There's still problems though. It still requires like very accurate setups. Like for example, this is an example of reconstruction of the city with drone footage. We do get like a pretty dense reconstruction of things in the city, but it's not very visually pleasing. We can't really show this as a complete model. It looks actually photorealistic as the final product. And here we jump to more recent advancements, like the AI take on 3D reconstruction. And this is something I worked with a lot. It's called NURFs, or neural radiance fields. The name doesn't matter. The point is, it's a new paradigm in representing 3D models. If you've ever looked at clouds in games or whatever, the approach is very similar, because now you represent objects not as just these point clouds or meshes from triangles. It's a function in space where you map every 3D points to a color and density. It's a very different approach. It is very hard to work with, to be honest, because to get the color for a single pixel, to get the render of a single image, you need 64 at least neural network calls per single pixel. It's very computationally heavy, very unusable for training something like this, because reconstructing a single scene is training this neural network. It takes on a pretty powerful GPU up to 2 days, so we can't use this. There's been a lot of progress. For example, NVIDIA put like this work called InGP, which greatly optimizes this. This was a huge leap, like the time in the 3D construction community. This was huge.
Excuse me? How is Gaussian splatting helping?
I'm going to talk about that. We're going to get to that. In the 3D reconstruction community, this was huge, because NURBS were very hard to work with, very not accessible. But now we can train like these very photorealistic, very reconstructions like this much faster on very much lighter GPUs. We can actually render this in real time, view these reconstructions. Because NVIDIA, they're really good at developing specialized CUDA kernels and specialized like embedding grids for the 3D this. But it's still problematic. It still requires a 3090 GPU to train. So there's still a lot of limitations in the NURF approach. And here's where we get to 3D Gaussian splatting. This is the latest approach. I don't know if you've heard. I don't know if you're like a 3D construction nerd like me. But this is the best that we have right now, basically. This is a new approach to represent 3D models, where we think about it not as a point cloud, not as a mesh, not as a volume. It's a combination of like these 3D blobs. The upright visualization shows that a model is like constructed from these like ellipsoids in 3D space. But if we put enough of them, like 300,000 into space, and try to comprise a scene out of them, we get very photorealistic scenes like this. Like to me, this looks like a real video of a scene, undistinguishable from something actually real. The approach to training and rendering this is much more optimized. It's like a discrete structure. The algorithm to render this, to convert this model into a render into 3D image, is very similar to what we use in regular software like games or whatever, or work with meshes. It's an algorithm called rasterization, and the approach here is very similar. We can render this in high quality 30 FPS. And the point is, this completely killed NURF. NURF was like big at the time. Now NURFs are nothing. It's very computationally heavy, very hard to view, very hard to work with. Gaussian splatting is much better in every aspect. NURFs are still good. I don't have enough time to talk about it, but NURFs are still good for generative AI. Specifically, there's lots of like companies that work into like, text to 3D, where you just say, yeah, I want 3D money, and generates you 3D money. NURFs are still applicable there, but for every other use case, Gaussian splatting is now mainstream. It's not very popular to use for representing 3D photorealistic models. For example, there's a bunch of examples of using it, trying to use it for game development, because in order to achieve like photorealistic scenes, something that looks very real, it's a lot of work to do with like traditional approaches, where you model the scene by hand, you try to apply materials, apply these like different tune the properties until it looks good, and also you have to like have a renderer that is very powerful. But here, you just put a scan into a game, you have like these very optimized renderers that are very easy to run, even on weak devices. So for example, this link leads you to a web game where you just can walk around like these big 3D Gaussian splatting maps. And I think it's cool. There's a lot of investment from big corporations into Gaussian splatting. For example, this is an example of the Samsung conference presenting their XR headset, and they also show that there's a Google Maps VR app where you can look at restaurant interiors, and they can afford to download a whole model of a restaurant and show it to you in real time, like this. This was again not possible with previous models. It was way too heavy, way too hard to render like in a photorealistic manner, but now this is possible. And if I don't know if you've heard the Apple Vision Pro personas, like the chats, you have basically it scans your face, it tries to show it to another person. This was confirmed, I think, pretty recently to also be using Gaussian splatting. That's good. And this is a from the PI that I scanned like a week ago. It was really easy to do. This was like a very lazy 20-second video. I just fed it into this like pretty simple Python framework called Nerve Studio. It can do both nerves, Gaussian splatting, whatever. It required like a pretty. It doesn't require a hard, like a powerful GPU. Very like fun to experiment with, and there's a software to like work with this to edit this model. For example, Adobe is now investing into Gaussian splatting because there's a lot of like, efforts in the art community to also work with these like this new Gaussian splatting approach for 3D models, for these photorealistic models, and yeah, I want to say still a word of caution because these models, they are very much about visually pleasing outputs, but not about accuracy. They imagine a lot of things for you. It looks nice, but then when you go to like an unexpected position, it breaks. Still, it's very cool. If used carefully, this is a very powerful tool. And I hope I showed you why this is powerful and cool. That's it for me. I talk about a lot of things, and I think there were questions from someone. I'm going to answer if you want.
Is it possible to replace CAD software?
Replace what?
CAD software, like SolidWorks, stuff like that. Because I know like the mesh, like how you do the math, it's not like, it's only the same outside texture, but it's not like, you can't actually model, for example, a bolt or like something that should be like, I don't know, in like an engineering standard.
You mean you can't model something like very accurate with parametrically? So no, this can't be really used parametrically. It's still like a discrete structure. When you have discrete structures, you can't like in CAD software. There's like this elliptic curves that you use to model. You use to model 3D models. With Gaussian splatting, it's still like a very discrete structure. You can't really use it for that.
Okay, awesome.
But there are a lot of interesting work to try to reconstruct from videos CAD models. It's complicated, but it's possible.
Yeah, I mean, it doesn't seem, I mean, it kind of works. It's not like, I don't think it's like it can replace, I don't know, like CAD engineers anytime soon, at least for my experience.
Yeah. Good. Can we get here?
Thank you.
Thank you.